Welcome to our today's lesson. We are going to look at thermal expansion, and in thermal expansion we are going basically to start with the first part, which is giving the definition of temperature, because we're going to look at thermal, a word that is related to heat, and expansion, as we know, is the maybe increase in size or volume. So we are going to look at thermal expansion, and as we've said, the first part is going to be the definition of the word temperature. And temperature is the degree of hotness or coldness of a body. So for us to be able to tell somebody that we are talking about temperature, then we must be able to give the degree of hotness or coldness of a body or an object. Then the temperature is measured by an instrument called a thermometer. And as we know, we have different types of thermometers, and we are going to look at them as we move on. But in this case, that is the instrument that we use to measure thermometer. Then we can talk about this temperature being a basic physical quantity and is measured in degree Celsius or the Kelvin. So once we look at this as a basic physical quantity, then we'll need to know the SI unit of the temperature. Temperature's SI unit is the Kelvin, abbreviated by that K there, which is a scalar quantity. It doesn't have direction, so it's a scalar quantity. I believe from our previous lessons in pressure, we can be able to differentiate between scalar quantities and vector quantities, whereby we said scalar quantities are quantities with only magnitude but no direction. For example, mass. And then we said vector quantities are those quantities with magnitude and direction. So that's why here we are saying temperature is a scalar quantity. It only has the magnitude. Moving on, we can talk about thermal expansion and contraction of solids, liquids, and gases. And to start with, we want to say that all substances increase in size when heated. That is the expansion we are talking about. This increase in size of a substance is called expansion. So probably you can see now that all the three states of matter experience expansion, and that's what we want to look at in this topic. And on the other hand, when a substance is cooled, it decreases. So there is two sides. One, heating a substance, there is an increase in size. We talk about expansion. Then this other side, we have cooling an object or a substance. Then we are experiencing decrease in size. Therefore, in this case, we are talking about contraction. So expansion in solids is the first part that we want to look at. We want to look at expansion in solids. So thermal expansion and contraction in solids can be demonstrated using a ball and ring experiment. We can see the setup that is given below. Now we want to start with this video here. We were to start with this so that we can be able to look at what is in this experiment. So at room temperature, as you can see, we have this ball being able to go through the ring that is shown, and as you can see, it's comfortably moving because at room temperature all of them are have not experienced any expansion. But once you hit that ball on this source of heat that we have here, the ball is not able to go through that ring. So in this experiment, we're trying to see how the ball, after being hit, expands, that is, increase in size, therefore not being able to go through this ring which was not hit. And in that case, we can see that experiment, that is the ball and ring. The ball should pass through the ring when both are at room temperature, and we have seen that. And when we hit the ball and try to pass it through the ring, we observe that the ball is not able to pass through. So that shows us that the ball had expanded. So in a descriptive form, we have the observation here. When the ball is heated, it does not pass through the ring, but when it is left on the ring for some time, it passes through. That means that when it's left on the ring for some time, it means that it cools. That is, contraction takes place, decrease in size. Therefore, it will be able to pass through. So when giving an explanation now, the scientific explanation under this observation will say that when heated, the ball expands and so cannot go through the ring. When it is left on the ring for some time, the temperature of the ball decreases and the ball contracts. At the same time, the ring absorbs some heat from the ball. Its temperature increases and so it expands, allowing the ball to pass through. So that is the observation and the explanation for the ball and ring experiment. And I believe you've seen how the ball is able to pass through at room temperature, but once it is heated, then there is increase in size, that is expansion. Therefore, it's unable to pass through. But once it's left there for a while, again we see another scenario of contraction, which means that now the ball will be able to pass through in due time or as we move on. Then now we have another experiment, which is the bar and gauge experiment. And in this experiment, we have a form of a question here. As you can see the diagram on our screen, we have the gauge, which is down here. You can see the red cursor. Then we have the metal bar up here. So now, at room temperature, this metal bar can be fitted perfectly inside this gauge. But then, once this metal bar is hit, then we are going to see a difference. So the question is that in the figure below, at room temperature, the bar fits into the gauge. So they are asking us, first of all, to explain what will happen when the bar is heated and you try to fit in the gauge. Now, in this question, I want us now to structure it in this form. First of all, let us state the observation before heating and after heating. Now, before heating, this metal bar would fit in this gauge perfectly. But after heating the metal bar, we expect the metal bar to expand. That is the increase in size. Therefore, it will not fit in this gauge. So that is the observation before and after heating. So our question is, we explain what would happen when the bar is heated and we try to fit it in the gauge. The bar does not fit in the gauge because it expands when heated. So expansion, which is the increase in size. So we are also having a situation here to consider, a case where the bar is slightly bigger than the gauge at room temperature. Explain what you will do to make the bar fit into the gauge. So I'll go back to the diagram. Now they are saying whereby we have the metal bar being slightly bigger than the gauge. In that case, we are expected to make sure that we increase the size of the gauge. How can we increase the size of the gauge? By hitting the particular gauge, and hitting will result to expansion. So we hit the gauge so that it expands and the bar will fit. And as you note that, as you can note, in this topic we have key terms that we have to use. For example, expand, contract. Once you've made an observation, then you are expected to use such terms so that you can be scientific and on point. Then we have another experiment that is for comparing expansion and contraction in metals. So we have an experiment sent to compare the expansion of some metals here. So look at the diagram that we have here. we have a clamp and the stand at this point. Then we have a metal bar which has been fitted on that clamp, the black one. Then on the other end, we have a pivot which has a pointer, and there is the direction of the pointer and a scale. The scale is from 0. So looking at this figure here, initially at room temperature, there is no deflection of this pointer on the scale at all. But once we start heating, then we are talking about increasing in size. This particular metal bar will expand. And once the metal bar expands, then that small change, which might not be visible by your eyes, will be noted by the deflection or the direction of the pointer. If it deflects here, then we'll be able to see or note that there is an increase in size, that is expansion, that there is expansion taking place. So this scale is very important so that we can be able to determine the degree or the extent of expansion of different metals. So moving on, now we can explain that particular experiment. We are asked to explain how the experiment works. So when the metal bar is heated, it expands and it pushes the pivoted pointer, and the reading is taken on the scale. Metal bars of the same size made of different materials are attached to the clamp one at a time and heated for the same length of time. The readings on the scale are recorded and compared. So this is an explanation of carrying out expansion for different types of metals. So in that case, you can see how we are considering metals of the same size and we are heating them for a given specific duration of time, which is same. Then we are taking the readings so that we can be able to see the extent of increase in size or expansion. So what are some of the precautions to be taken to ensure there is a fair result? So first of all, the metals should be of the same length and diameter. Then the second precaution, the metal should be heated using the same burner because of the strength of the flame. Then we have the other one, the metal should be heated for the same length of time. If we decide to heat for 5 minutes, then all the metals to be used in the experiment should be heated for that particular 5 minutes, so the same length of time. Moving on from that particular point, we can now look at linear expansivity, having looked at that comparison of expansion and contraction. When we talk about linear expansivity, it is the tendency of a material to expand when heated. So different materials have different linear expansivities, meaning that their rates of expansion or contraction are not the same except a few materials. So you can see this particular table that we have here. We have materials and their linear expansivity. So we have aluminium, which is the highest here. It has 26 times 10 power negative 6 per Kelvin. Then we have brass, copper, iron, concrete, steel. Now, this gives us an insight of which material expands more than the other. Definitely, a good number of materials expand, but once we know a particular material's linear expansivity, then we can be able to know which one expands or contracts in a certain rate. So now that brings us to our another section, which we are going to look at what we call the bimetallic strip. And in this section of bimetallic strips, we want to look at first of all what a bimetallic strip is. Then now we consider the behavior of a bimetallic strip in different temperature situations. We'll first of all look at it in the room at the room temperature. Then we can be able to look at when temperature is increased and when temperature is decreased, that is heating and cooling. So bimetallic strip is made by riveting together two metals which are of different linear expansivities. So different metals which expand differently or expand at different rates. That's what we're calling linear expansivity there. So we want to see, once they are riveted together, how do they behave? So the metal which expands at a higher rate when heated contracts faster when cooled. So this is one of the key points which is going to help us in this section, that the metal which expands at a higher rate when heated contracts faster when cooled. So let us put it in our minds that once we have noted metal which expands faster or at a higher rate, it is still the same metal which will contract faster when cooled. So we want to consider a bimetallic strip made of iron and brass at room temperature and pressure. In the figure below, we have these figures here. Part A, we have brass has a higher linear expansivity. At room temperature, we have this brass and iron riveted together and they are very straight. There is nothing that has taken place. But now we are saying brass has a higher linear expansivity than iron. I believe we had seen that from the table here. Brass is at the second position here. It has a higher linear expansivity than iron, which means when heated, brass expands at a higher rate or faster than iron. Then definitely when cooled, brass contracts faster than iron. So now in this section here, we are told that brass has a higher linear expansivity than iron and therefore expands at a faster rate than iron. So when the strip is heated to a temperature greater than room temperature, it bends towards iron as shown. So during heating, we have this one. We are saying brass expands at a faster rate. So it means it will increase in length more than iron. In that case, it will be longer. Therefore, this particular bimetallic strip will curve towards where we have the metal or the material with a lower expansivity rate, which is iron. So it will curve in that way and brass will be from the outside. What about when it is cooled? So when the strip is heated to a temperature greater than, we have already seen that. And when we're saying when the strip is cooled, it bends towards brass. So in this second figure here, this bimetallic strip is cooled. When we are cooling it below room temperature, then we are saying that the material that expanded at a higher rate or faster now contracts at a faster rate. So it contracts, it reduces in size, the length decreases. Therefore, this bimetallic strip curves towards the side of brass, hence having this shape here. So brass will be now on the inside and iron from the outside. So that is the explanation for this bimetallic strip. Still, we have the figure below showing bimetallic strip at a room temperature. We have now aluminium and copper. We want to draw the bimetallic strip when at 90 degrees. 90 degrees, that is far beyond room temperature. Therefore, it means that it has been heated. This bimetallic strip will be heated. As we saw earlier on in the table, that is the linear expansivity, we realize that aluminium has a higher linear expansivity than copper. Therefore, in this case, when heated, aluminium will expand at a higher rate than copper. Therefore, it will increase in length. It will be longer than iron. Therefore, the shape that we expect of this particular bimetallic strip will be of this form, whereby now the shorter one, which is copper, will be in the inner part, and then aluminium, which now expands more, is from the outer part. Moving on, these are different pictures here for a bimetallic strip. One is to show the heating process. There is heating the strip here. Then the other one here we have for cooling the strip. So in this case, you can realize that the material B expands more than material A. Therefore, we are having it curve upwards. And in this case here, we are realizing that the same material B, since it has a higher linear expansivity, once it's cooled, again it contracts faster than A. Hence the shape that we are having here. So we still have all those here. We still have one for brass and steel. On heating, you realize brass has a greater or a higher linear expansivity rate than steel. Therefore, on heating, brass expands more than steel. Hence this shape. Same case on cooling, the brass which expands faster or has a higher expansivity rate, then is going to experience contraction, or it's going to contract faster than the steel. Hence this particular shape that we are having. Then moving on, we talk about when temperature increases above room temperature, aluminium definitely is expected to expand faster than copper. This is now the answer to that particular question. Then we can be asked to draw the bimetallic strip when at negative 25 degrees Celsius. At negative 25 degrees Celsius, that's far much below the room temperature, and it is expected that aluminium, which expands faster than copper, will also contract faster than copper in this case. Therefore, this will be the shape with aluminium on the inner part of this bimetallic strip and copper on the outer part. So when temperature decreases below room temperature, aluminium contracts at faster rate than copper. Now, we are at the point where we are looking at the applications of expansion and contraction of solids. And the first case, we are talking about expansion joints in steam pipes. Now, when carrying steam, pipes carrying steam are fitted with loops or expansion joints to allow for expansion when steam is passing through them and contraction when they are cooled without the loop. The force of expansion and contraction will cause breakage of the pipes. So now these loops are here majorly to help in expansion and contraction. So these pipes carry steam, and you remember steam is of a very high temperature. So they have loops or expansion joints to allow for expansion when steam is passing through them and contraction when they are cooled. Without the loops, the force of expansion and contraction will cause the breakage of the pipes. That's why we have these particular shapes in the steam pipes. Moving on, we can talk about fixing of railway lines. Railway lines are constructed in sections with expansion gaps, and the sections held together by fish plates. The bolt holes in the rails are oval to allow free expansion and contraction of the rails as the bolts move freely in the holes. So we can look at a modern method of allowing for expansion and contraction in railways is to plane slant the rails so that they overlap. So looking at this first figure here, we have a gap left between this first plate here and the second one. Looking at this fish plate that is connecting the two, this one and this one here, there is a gap that has been left here, and then we have bolts fitted at this particular point. Remember, we have said that the bolt holes in the rails are oval. So these holes here, they are oval, so that once expansion and contraction takes place, it can take place freely. So to allow free expansion and contraction of rails as the bolts move freely in the holes. Then we have this modern one, whereby we've said a modern method of allowing for expansion and contraction in railways is to plane slant the rails so that they overlap. So look at this overlap here, a very big gap in between. Once this expands, it can move to that side, and this one moves to this side. Therefore, there will be no breakage here. They'll just expand and fit this gap that has been left here, that is overlapping rails. Then you can see the bolt holes which are over here when the fish plate has been removed. So that is for the railways. A very good example here. These are modern railway. You can see the figure here. These are the gaps left. This is the fish plate, and these are the oval bolt holes. They are oval. You can see that. Very good example for us. Then we can move to fixing of steel bridges. In bridges made of steel guards, one end is fixed and the other end placed on rollers to allow for expansion and contraction. A very exciting application here. You can check this bridge here. On this end, it is fixed, but on this other end, the bridge is positioned on rollers, placed on rollers. We know rollers can allow something to move. So once it expands, it can comfortably move to this side without bending or causing any breakage. There will be no cracks in these pillars for the bridge. Therefore, that is allowed, or it's as a result of these particular rollers. So this is also a very good application. Then we have rivets. Thick metal plates in ships and other structures are joined together by means of rivets. Um, a rivet is fitted when hot and then hammered flat. On cooling, it contracts, pulling the two plates firmly together. So these ones for students, you can actually check even your seats, fixing those backrests. You can see they have used rivets, two plates which have been tightly tightly held together by a rivet. So it works through the principle of expansion and contraction. Then we have installation of telephone and electricity wires. Installation of telephone and electricity wires. Now, they are loosely fixed to allow for contraction. Then now, telephone or electricity wires appear to be sharper and taut in the morning, but when it is hot, the wires appear longer and slackened. Now, if you look at those electricity wires in the morning, they appear this way. They are sagged. No, in the morning they appear very firm because they are cold. They have contracted. But as the day moves on, as the day progresses, as we have more heat in the atmosphere, then these wires expand, hence appearing to be sluggish or sagging. So we have this. Then the next part we want to look at is the bimetallic strip. That is one of the most common applications of the bimetallic strip, and is in the thermostat. A thermostat is a device for maintaining a steady temperature. The thermostat shown below is used for controlling the temperature of an iron box. A heater circuit is connected through um, the circuit there. So you can check this figure here. We have this bimetallic strip. We have the iron, the lower side, and the brass at the lower side, while iron is at the upper part. Then we have the contact here. We also have the terminals here. Then the insulator at this particular point. Then knobs for setting temperatures. So how does this bimetallic strip work? We want to see how it's going to work so that we can see this contact here being closed, so that means it's either going to curve downwards or upwards so that it can complete the circuit or break the circuit. So let us see. The If the iron box becomes too hot, the bimetallic strip bends, curving away from the lower contact. This breaks the contacts and the circuits of the heater. When it cools, the bimetallic strip bends, closing up the gap between the contact and the heater is switched on again. So that figure we are looking at here, if this room is or if the temperature is too high, then this brass will expand and become longer than the iron. Therefore, it will curve away from this contact. Therefore, we'll have a breakage, contact being broken here. And then if temperature is low, then again brass will contract more. Therefore, it will contract downwards. Therefore, it will curve downwards and will close the contact. So we are saying if the iron box is required to be very hot, high temperature, the setting knob is adjusted to push the metal K such that the contacts are tight together. For low temperature range, the adjusting knob is released so that the position K is lowered. Now, the thermostat is also used to control the temperature of electric cookers, electric heaters for warming rooms and fridges. So all these appliances here apply this concept of the thermostat in their working. So we have looked at the iron box, which has that thermostat. Then we have this one for the rooms, electric cookers, electric heaters, and for warming rooms and fridges. They all apply that concept of bimetallic strips under the thermostat. Then we have this expansion and contraction of liquids. So in this case, we are purely going to look at liquids. And to demonstrate expansion of liquids, we first of all want to consider the flask below, which is filled with the colored water as shown below. So we have heat at this particular point. This is water and the water level at this particular point. Now, before going through what we have here, I want us to check. This video here. So check this video here. We have a liquid in that flask. Initially, it is at volume V3. It is heated. Initially, the flask expands first, then the level of the liquid in the tube falls. Then after some time, the liquid in the flask is heated, then it expands, and as you can see now, the level of the liquid is going up. That means that liquids also expand, but initially you saw that as we started, that particular flask expanded faster than the the liquid. So when the flask is heated, it is observed that water in the glass tube falls slightly and then starts rising. So initially it falls, as you've seen in that video, then after some time it starts rising. The initial fall of the water level in the tube is due to the expansion of the flask, which gets heated first. Then the water starts expanding. When heat finally reaches it and it rises up the tube, since liquids expand faster than solids. So once the liquid has expanded, now the water starts rising up the tube. So from that point, you can say now different liquids expand differently, i.e., they have different rates of expansion. If the above experiment was repeated using alcohol and then methylated spirit for the same length of the time and using the same heater, it would have been noted that methylated spirit expands most, followed by alcohol, and finally water. So that is a very good example there, because once you look at that flask, a question can be asked. You state and explain the observation made. State and explain the observation made in this figure. So the student first of all is expected to state what they see. The observation is purely what you see. First, you will say that the water in the flask tube falls slightly and then starts rising. That's what you can see. Then you start explaining it. So observation is purely something that is visible, what you saw. Then once you are explaining, then you will now give the reasons why the water is moving down or falling slightly and then starts rising in that case. So moving on, we can look at the next part, which is anomalous expansion of water. Under anomalous expansion of water, this is the unusual behavior of water in which it contracts when heated and expands when cooled between 0 and 4 degrees. So we want to consider heating ice from -8 degrees until it changes to water and its temperature increases to 8 degrees Celsius. A plot of volume versus temperature for the water is as shown in this figure A. So if the temperature is -8, as you heat, you realize that the volume it keeps on increasing to 0 degrees, but as it's moving from 0 to +4, we have the volume, we are having the volume decreasing. So in that case, we are having the volume from this point here decreasing as we are increasing the temperature up to 4 degrees, where again the volume starts to increase. So that is the graph for volume against temperature. Then there is another one for density versus temperature, whereby we have the temperature decreases as the density decreases as temperature increases. So from -8 all through, we are having density decreasing up to 0, whereby as now the temperature increases from 0 up to 4, we are having the density increasing. Then as from 4 degrees Celsius, we are having the density decreasing. So what are some of the effects of this unusual behavior of water, what we are calling anomalous expansion of water? First of all, you realize that it's able to support aquatic life in polar countries during the winter. Now that during the winter we have water freezing into ice. So the ice being less dense than water, it floats on water. So this ice that has floated on water is a poor conductor of heat. Therefore, it assists in insulating the water below against heat loss to air above it. So this insulating property of ice ensures that the aquatic life like fish and other submarine animals and creatures living there are able to survive below there because temperature is not lost. Moving on, we can, that is the figure to explain, this is ice at 0 degrees. Below it, we are having temperature to 4 degrees. It's not lost because ice is a poor conductor. Insulates. Then anomalous expansion of water leads to formation of icebergs, which pose a great danger to ships. Then it causes weathering of rocks, since when water trapped in freezes, it expands, thus breaking rocks into small pieces. So if water is trapped inside cracks of rocks, then it can freeze to form ice, and this will expand, thus breaking the rocks into small pieces. Then it can also cause bursting of water pipes when water freezes in them. So now, what about expansion of gases? We have an experiment to demonstrate expansion and contraction of gases. And as you can see, we have water in a container here. Then we have a flask which is inverted with air. It has air, and there is this tube here downwards into the liquid. Now, what happens when air inside this tube is heated? Now that one will help us make an observation and know that indeed air can expand or contract. Now, when the flask is warmed, it is observed that the level of water column inside the glass tube drops, indicating that the air has expanded. So, if we hold this flask here with warm hands or use some other form of heating to heat this flask here, then we realize that the water level here will not be at this point here now, it will move down. Reason being, the air inside the flask will expand, and we said expanding means increase in volume. So the volume of this air will increase, therefore we'll have more air trying to escape, therefore pushing this level of water down. So we are saying when the flask is warmed further, so if we continue warming, some bubbles are seen at the end of the tube in the water as air escapes from the flask. So we'll be seeing air bubbles here trying to escape. So when the flask is cooled, water level is observed to rise. So if you cool this flask here, then the water level in this tube will be seen to rise, because cooling means contracting, and once we contract this air, the volume occupied by the air will decrease. Therefore, it will create more room for this water to rise into this tube. Therefore, we are saying when the flask is cool, water level is observed to rise up the glass tube because the air inside the flask contracts to create space. Moving further, we have an example here. The figure below shows a beam balance made out of concrete and reinforced with steel. We want to use the diagram to explain the behavior of the shape of the beam when heated up. So this is the beam with concrete and steel. The beam expands linearly. The beam remains straight but longer than before heating. Both concrete and steel have the same rates of expansion. Their values of linear expansivity is 11 times 10 power negative 6 Kelvin. So concrete and steel are always used because they have the same rates of expansion. Then we want to state two liquids which are used in a thermometer. One of the liquids we have alcohol and the other one mercury. Then with a reason, state which of the two liquids in given above is used to measure temperature in areas where temperatures are. Part 1, below negative 40 degrees. When the temperature is below negative 40 degrees, we are going to use alcohol because it has a low freezing point, that is of negative 115 degrees Celsius. So we should be very keen on that. Then where temperatures are 150 degrees, we are definitely going to use mercury because mercury has a high boiling point, which is 357 degrees. Then now we also have some other terminologies here to define what we understand by the term lower fixed point on a temperature scale. So lower fixed point, this is the temperature of pure melting ice at standard or normal atmospheric pressure. Now we want to name two adaptations that can be made to a mercury thermometer to make it more sensitive. So we definitely have to look at the bulb. It must be made of thin walls. So using a thin walled bulb, this will increase the sensitivity to maybe the temperature of the surrounding. Then talk about the capillary tube. We are supposed to now look at how we can narrow the capillary tube so that it can also be sensitive to temperature. Then moving on, we give a reason why concrete and steel do not crack when subjected to changes in temperature. We give a reason why concrete and steel do not crack when subjected to changes in temperature. As we had said, both concrete and steel have the same rates of expansion, and their value of linear expansivity was seen to be 11 times 10 power negative 6 Kelvin. Therefore, they will expand uniformly when heated. Then aquatic animals and plants are observed to survive in frozen ponds. We explained this observation. We said water freezes and the ice formed floats in the water because its density is less than that of water, then insulating water below it. Now this temperature is able to help the aquatic animals survive because of this behavior of water. Now we have some revision exercise here, whereby we have a number of questions, and these questions are in our KLB book 1, and I request that learners to move to that book and try to answer questions. And as you can see, most of the things we have covered are here, so that one will help you work out this part. Thank you.